Good afternoon to all. Last few class we are discussing gravitation, gravitation law, Kepler's law of gravitation, universal law of gravitation. After that, acceleration due to gravity, that small g formula. So small g is equal to capital G m divided by r square. So capital G means gravitational constant. The value of gravitational constant 6.67 into 10 power minus 11 Newton meter square kg minus 2. So this is the value of capital G. And what is the value of Earth radius? That is R value. 6,380 kilometers. 6,380 kilometers. Sometime in problem they will mention the value of radius in 6. Just a minute. Hello, my body. My voice is audible, ma? Hello.
Yes, sir. Audible, sir.
Okay.
Sir, audible, sir.
Thank you. Thank you. Sometime that radius of Earth, they will give 6,400 kilometers also. So depends upon the problem. After that, there is small g value. Small g means acceleration due to gravity. It is a 9.8 meter per second square. The variation of acceleration due to gravity, the effects of height, the effect of depth, the effect of shape, the effect of rotational motion. So all the formulas also we discussed. So after that, the mass and density of Earth. So how to measure the mass? How to measure the density? The mass of the Earth 5.98 into 10 power 24 kg, and density value 5.5 into 10 power 3 kg meter minus 3. Next one we discuss gravitational field. Next, intensity of gravitational field. So intensity of gravitational field means the force experienced per unit mass. Okay, so E gravitational is equal to F by M. The gravitational intensity, it is equal to acceleration due to gravity, because you will get both two formula also similar. Okay, so now today class we will discuss gravitational potential energy. Just a minute, I will share my screen. Please mute yourself now. So please everyone note it now. I will explain after. Gravitational potential energy. Please mute yourself. Okay. Gravitational potential energy. Okay, GPE means gravitational potential energy. Please note down the definition. I will explain. Of your body as the amount of work done bringing the body from infinity to okay. So gravitational potential energy. Okay. Of a body at a point defined as the amount of work done bringing the body from infinity to that point against gravitational force. Okay. So now I will draw one small diagram for the concept. It is easy for you. So consider this is our Earth. Okay. Now one small object it is there. Object or body both also similar. Okay. Now I want to bring in this object point B to point A. So against to gravitational force. So it is called as gravitational potential energy. Everyone draw the diagram now. So this is our Earth. In center of the Earth, it is O. Mass of the Earth, capital M. From origin to P, the distance is x. I consider one more point. This is A. From origin to up to A, the distance is small r. Okay. So actually this is in the infinity point. The mass of the object m, small m. This is capital M, this is small m. And in between, I will move just one small distance, that is a dx. Okay. Now listen, the gravitational potential energy is no potential energy. It is positive when two masses are in repulsive in nature. M1, M2. It is in the repulsive nature. So repulsive nature means this is also plus, this is also plus. Otherwise, this is also minus, this is also minus. So in this condition, it is in the repulsive nature. So now potential energy is positive. Potential energy value, it is negative. So two object M1, M2. This is plus, this is minus. Otherwise, this is minus, this is plus. Then you will get attractive nature. Please note down now. Okay. So next one, this is a point 1, this is point 2. Third point, now that M1 small m, it is no. So the object at infinity, the gravitational potential energy, it is 0 at the infinity. So what is the value of gravitational potential energy? Means it is 0, the point of infinity. So it is called as zero potential, otherwise zero level of potential. zero level of potential energy. Okay. Fourth one. So from the diagram, fourth one, we should find the gravitational potential energy up to R. Gravitational potential energy up to small r distance. Second condition, gravitational potential energy up to h. Which point is h means? The entire value. So fourth point, the gravitational potential energy of a body it is denoted U, of a mass small m at a distance, please mute yourself, at a distance small r. Okay, then you will get U equal to minus capital G, capital M, small m divided by R. Because in this R, it is considered to from the center of the earth. Gravitational potential energy of a body mass m at a distance r. So U is equal to minus G capital M small m divided by R. So what is R here? From the center to one particular height. I'm getting some disturbance now. Please mute yourself. Okay. Fifth point. Listen. This is our Earth. Okay, Earth radius R. Now one more object is there. This is small m. From the Earth surface to this m. So we know that this is the x. So overall value, otherwise I will mention as h. R plus h. So U equal to minus G capital M small m divided by radius of the Earth capital R plus h. So Earth surface to in this particular height, it is called as h. So first form, fourth formula, they will give directly now. This is small m, this is capital M, This is R. So like that it is means you can use U is equal to minus capital G capital M small m divided by R. In case they mention in surface of Earth to 200 kilometers above the Earth surface, 200 kilometers above the Earth surface, then what is the potential energy? Like that they are asking means in this 200 kilometer plus the radius of Earth 3600 no 36 around it will come 3400. 380 kilometer. So now you get an idea about so how to use in these two formulas, fourth formula and fifth formula. Please note it. Just a minute, ma. It is loading.
Gravitational potential energy and gravitational potential. Objective: to derive the mathematical expression.
My video was audible, ma. Hello.
Sir, audible, sir.
Yes, sir.
For gravitational potential energy and gravitational potential. There are two types of forces in nature: conservative and non-conservative. Non-conservative forces like friction cause energy dissipation into the universe. Conservative forces like spring force lead to the conservation of mechanical energy into a system. Gravitational force is a conservative force, hence change in gravitational potential energy is defined as work done against the gravitational force. When a mass near the Earth's surface is raised through a small height, the gravitational force mg acting on it may be treated as constant. As the gravitational force acts against the direction of displacement, work done by it is expressed as minus mgh. Therefore, the change in gravitational potential energy is equal to mgh. In case of a satellite which moves to a higher orbit, the gravitational force it experiences varies throughout its path, as there is considerable change in satellite's distance from the center of the Earth. So how is this change in gravitational potential energy calculated when gravitational force is not constant? Consider a point mass m1 at O and another point mass m2 at A. m2 is moved from point A to B. Initial distance between them is r1. The distance after m2 moves to B becomes r2. Consider the particle moving through an infinitesimally small distance dr from C to D. The gravitational force at point C is minus g m1 m2 by r square r cap, and its displacement is dr r cap. The change in gravitational potential energy when the particle moves from C to D is negative of the work done by the gravitational force. Hence, du equals to minus f bar dot dr bar. Substituting f bar, we get du equals gm1 m2 by r square dr. The total increase in gravitational potential energy of the particle when it goes from A to B is integral gm1 m2 by r square dr from r1 to r2. Upon integrating and substituting the limits, we get delta U equals gm1 m2 1 by r1 minus 1 by r2. Conventionally, when the separation between the particles is infinite, we choose gravitational potential energy to be zero. The potential energy when the separation between the particles is r.
Please note down in this formula, ma. Del U equal to G m1 m2 into 1 by r1 minus 1 by r2. In case they are giving the limit. Now we consider that 1 by r2 it is a infinity line. Please note down the formula. Del U equal to del U or U both also similar. G m1 m2 1 by r1 minus 1 by r2.
Is calculated by substituting infinity in r1 and r in r2, which results in ur minus u infinity equals gm1 m2 1 by infinity minus 1 by r. Hence ur, The gravitational potential energy of the system is minus gm1 m2 by r. So gravitational potential energy is defined as the amount of work done in bringing a body from infinity to a given point under the influence of the other body. Gravitational potential due to a point mass. Gravitational potential at a point is defined as negative of work done by gravity in bringing an imaginary unit mass from infinity to that point. The gravitational force due to a point mass m on a unit test mass of say 1 kilogram at point C is gm into 1 by r square. The potential due to m at a distance r from it is equal to minus integral gm by r square dr from infinity to r. We take the constant term out of the integral on integrating and substituting the limits we get Vr equals minus gm by r. Hence gravitational potential due to a point mass m at a distance r is minus gm by r. Summary.
Listen, for the point mass. So point mass means we consider 1 unit or 1 kg like that. That is m, it is a last formula. G capital M small m divided by r. The small m value 1. So you will get V is equal to minus gm divided by r. So r means what? See here, from the center of the object 1 to object 2. So we consider this is the earth, no? So what is the radius of the earth? That is a capital R. So after that we are measuring with the H. That is the second formula, R plus H. Capital R plus H.
Distance r is minus gm by r. Summary. Gravitational potential energy of 2 point masses m1 and m2 separated by a distance r is minus g m1 m2 by r. Gravitational potential due to a mass m at a distance r is minus gm by r.
Okay, now we will discuss the escape velocity, another one orbital velocity.
Escape speed, orbital speed, and total energy. Escape speed. A cannonball shot upwards reaches a maximum height and returns to the surface of Earth due to the gravitational pull of the Earth. The ball attains a greater height if it is shot with greater speed. Greater the initial speed, further the object moves away from the Earth. At a certain optimal speed, the object just escapes the gravity.
Listen. So I am throwing the object. Okay, it is around initial velocity 50 kilometer per hour in vertically. It will go up. So after the certain height, the final velocity becomes 0. So again return back into the earth. In case maximum is what happened, so the same place it is not there, it will fall down. So like this happen, escape velocity means it will escape from the earth surface. Not only earth surface, that gravitational also. Escape from the gravitational field.
Gravitational pull of the Earth. This optimal speed is called escape speed.
Escape from the gravitational pull. Certain region gravitation is there. So after that there is no gravitation. So we want to throw maximum that point.
We will now calculate escape speed by applying the law of conservation of energy. Consider an object of mass m with an initial speed u on Earth's surface, and when it reaches a height h, let its speed be v. The initial total energy of the object when it is on the Earth's surface is equal to the sum of its initial kinetic energy and potential energy. And when it is at a height h, the total energy of the object is equal to 1 by 2 mv square plus minus gmem by re plus h. When initial speed is equal to escape speed, the speed of the object at infinity is 0. According to the law of conservation of energy, the total energy of any object on the surface of the Earth should be equal to its total energy at infinity. Thus, 1 by 2 mv square plus minus gmem by re is equal to 1 by 2 m0 square plus minus gmem by re plus infinity, which is equal to 0, or 1 by 2 mve square is equal to gmem by re. Thus, escape speed equals square root 2 gme by re. By substituting the value of gme and re, we get the escape speed from the Earth's surface as 11.6 kilometers.
Okay. So anything is throwing 11.6 kilometer per second. So definitely it will reach out of the Earth surface. That is the gravitational pull. V is equal to 11.6 kilometer per second. So within the seconds you want to throw 11.6 kilometers. Fraction of second, just to image it.
Per second. Orbital speed. The speed of any astronomical object in its orbit is known as its orbital speed. All planets in the solar system do not have the same orbital speed. We will now examine the factors which affect the orbital speed of a planet. Consider a planet of mass m revolving with an orbital speed v0 around the Sun in a circular orbit of radius r. The centripetal force necessary for the rotation of the planet is provided by the gravitational pull of Sun. Therefore, the centripetal force on the planet must be equal to the gravitational force on it due to the Sun. mv0 square by r is equal to gm m by r square. Thus, orbital velocity equals square root gm by r. The time period of the planet to complete one revolution around the Sun is equal to the circumference of the orbit divided by its orbital speed. Hence, time period t is 2 pi by square root gmr to the power 3 by 2. Total energy of a planet. We now
Listen the concept, ma. Again, I will tell you the formulas, how to use the formula, all the things. Okay, you get idea. Orbital velocity means what? Escape velocity means what?
know that orbital speed of a planet is equal to square root of gm by r. Hence, kinetic energy of the planet would be 1 by 2m into square root gm by r whole square. Thus, kinetic energy is gmm by 2r. The potential energy of the planet is minus gmm by r. The total energy of the planet is equal to sum of its kinetic energy and potential energy. Hence, total energy is minus gmm by 2r. Summary. Escape speed VE on a planet of mass m and radius r is equal to square root 2 gm by r. Orbital speed V0 of a planet revolving around Sun in
One more thing, satellite, ma, just a minute. It's not that, ma, we'll see gravitational field, okay?
gravitational field. Objective. Mathematical expression of gravitational field. Imagine a ball oscillating on the surface of a serene pond with still water. Another ball at a distance gets disturbed by the ripples created by the first ball. Similarly, every object in space, by virtue of possessing mass, creates gravitational ripples around it. These gravitational ripples create a vector field around the object. This field signifies the attractive force experienced by other masses in it. Let a test mass m experiences a gravitational force F bar at a point P. Gravitational field E bar at P is defined as the gravitational force experienced per unit mass. Therefore, E bar is equal to F bar by m. The SI unit of gravitational field is Newton per kilogram. Gravitational field due to a point mass. Consider a point mass m placed at point O. Let the mass m create a field E bar at point P. Then an object of mass m kept at P experiences a force m E bar. But from Newton's law of gravitation, the force on mass at P due to m is gmm by r square towards O. From two equations, m E bar is equal to minus gmm by r square r cap. Hence, gravitational field due to point mass m at P is minus gm by r square r cap. Summary. 1. Gravitational field is defined as the gravitational force experienced by a unit mass at a point. 2. Gravitational field due to a point mass is minus gm by r square r cap.
Okay, thank you so much. Again, we'll meet next class. Take care. Bye.